Okay, so we will continue this marvelous behavior track with one very cool talk about really technical stuff on behavior trees from the guys at Bohemia Interactive who works on simulations. So Martin and Uri will talk to you about really cool stuff.
Hello. In this talk, we are going to talk about reusability and abstractions in behavior trees. We will first start by explaining why we even need reusability or abstractions in behavior trees. Then we will talk about simple behavior tree reuse, and continuing and expanding on that, we will tell you how to implement parameters and local variables. Throughout the talk, Martin will be giving you motivation and talking about problems from a designer's point of view. And I'll be describing our solution and how we address those problems in the engine.
All right, so to start with a little bit of context so that you have a more insight into what we do, we don't actually do traditional video games, we do virtual training. What is virtual training? It's basically video games, but with not a purpose to entertain, but to teach people. So there are many applications, mainly in military law enforcement, but also in mining, medical training, and things like that. So basically it's a video game. We provide a sandbox tool where you can build scenarios, training scenarios, so the customer can heavily modify the game, he can add their own content, he can build missions, and then the trainees play through the missions, they can evaluate the decisions that they made, and the trainer can show them where they've done wrong, where they've done good, what they need to improve. And it's basically a low-cost alternative to real-life training, which in the military is very expensive because you need to roll out the tanks, the jets, and organize a lot of people together. It's much easier to sit them down in a classroom, sit them in front of a computer game. So our flagship product is called Virtual Battle Space. It's based off the Arma games. If you've seen them, it looks a lot similar. And the unique challenges that we have to face is that we develop this product very continuously. We continuously add new features, and we never fully know what will be our exact roadmap for 2 years from now, 3 years from now. So our all systems need to be heavily extensible. They need to be ready to tackle whatever the customer requests from us. And it's no different for the AI. So that is kind of the prime motivation for our system. It's also made a bit more difficult by the fact that our customer can become basically a modder. So we provide modding tools for our product, and then they can add their own content, and that still needs to work with our built-in systems.
To make it simple for our designers and later for third-party developers to configure our AI, we have chosen to use behavior trees as our AI architecture. And we understand behavior trees as a graphical programming language. It already has some structured programming features, as it allows sequences, selection, and iteration. And in many implementations, it also supports a form of subroutines or reuse, but this reuse is usually limited by being non-parametric. And while we have implemented most of the features in our behavior tree system, we took inspiration in existing programming languages. This way we could benefit from decades of evolution and experience in those languages, and just taking a full feature from a programming language, we already know what are the use cases for the feature, the implementation details, semantics, and everything is solved for us for free, and it just works. Another benefit is that designers or users are familiar with those features and can use them right away. Inventing features from scratch would be just too risky and costly. In our system, we have entities, and each entity has its own blackboard. That's a place where behaviors can store custom values. For example, entity mood, like how threatened it feels or how many enemies it's seen recently. Our behavior trees are all immutable themselves. This allows us to share one tree between multiple entities, and each entity only contains a state of evaluation for the tree. For example, which nodes are currently running, like which node is currently selected in a sequence. Sorry, I almost forgotten. We have an embedded Lua scripting which we use for parameter evaluation for nodes, for trees, to perform actions and also to evaluate conditions.
Mm-hmm. So to better illustrate the point, so it's using the actual implementation that we will be talking about. So let's move on to the actual behavior tree. So this is the whole behavior tree describing the behavior that we've just seen. So what we have there is we can see there's the retreat behavior on the left. So the orange node in the middle is a selector. So it selects between the retreat, the engage in the middle, and the least priority one, the patrolling behavior. And we can already see in this very small, very simple tree that there's code repetition. So there's twice I had to implement the firing and twice I had to implement the movement behavior. And it would be obviously better if I could implement it only once and then somehow change the code in one place. I would have a smaller decision tree. So we can already see the disadvantages of the simple system, where for such a simple behavior, we would have difficult tweaking. I would have to change the code in two places. If I had more designers working on this behavior tree, then they would all be changing the same source file, could easily create conflicts. So obviously, we need to be able to reuse the behavior tree somehow, and that's what Juraj will be talking about.
So reuse in programming languages is usually solved by defining a function and then later being able to call that function in other places. Or it may be solved by macros, but I'm not going into details there. Function call may use static or dynamic dispatch, while static is known at compile time or at load time which specific function will be called. With dynamic dispatch, the function is determined by some runtime property like object type. Tree can be understood as coroutine, or it's really similar to a coroutine in a programming language coroutine is a generalization of a function, which just means it's a function that can interrupt itself and then it can be resumed. In our system, we implement a function call operator by a reference node. It's a special node that's a leaf node in its tree, but it acts like a decorator for the target tree. The target tree is referenced by name, and it's checked at load time that the target tree is valid. So even before the tree runs, we know that it actually can run. An implementation detail is that by resolving reference nodes at load time, we can store a direct pointer to the root of the target tree, so that there is no need to do any runtime search by name. And after resolution of all reference nodes, the trees actually become oriented graphs, which might actually contain even cycles because we don't forbid recursion.
Mm-hmm. So after revisiting my original behavior tree and replacing my reusable behaviors with reference nodes, I've been able to bring it down in size a little bit. But if we add the actual subtrees that the movement and firing expands to, we can see that I haven't helped myself very much. Well, I have helped myself in some concerns. That's I now have the separation of concern that I wanted. So I have a specific implementation of firing. I have a specific implementation of movement. So I can have multiple people working on it, changing just one part of the behavior. But the problem is I don't want the same movement all over the tree. We've seen that the soldier moves differently when he patrols. He moves differently when he retreats. He engages differently when he retreats. He engages differently when he tries to kill the enemy. So what I would like to do is somehow parameterize the subtrees that I want to call. I can do that already within this simple system by storing the parameters in the blackboard, in the global memory, but that has several drawbacks that I will talk about now. So basically, storing parameters in a blackboard would be equivalent to storing parameters in global variables in basic programming languages, which we all know is bad. It leads to bad encapsulation. It leads to user error. Somebody can override the parameters before they get to the function where I actually need them. And it's obviously error prone. And for designers, we want to make the system as easy as possible. There's also one more interesting drawback, and that's if we store the parameters globally, we can't reuse the same tree in parallel execution. So I've prepared a small example to illustrate that because it's not so straightforward. So what the tree that I have here, it's a variation of what I was showing. So basically it selects between a flee, engage, and move behavior. And we can see on the right, it uses two subtrees for detecting either threats or targets to engage. And that's the same subtree, I just want to pass different parameters to it. So if I were passing the parameters through Blackboard, then obviously there is no way to pass different parameters to the same function call that I want to behave differently while it's running some side by side. So we need a way to pass parameters explicitly to the reference node, just like a function call that we all know from common programming.
To make our behavior trees parameterized, we took heavy inspiration in how parameters work in other programming languages. Same as in programming languages, parameters are a property of function definition. Here, parameters are a property of a behavior tree. We implement name parameters. That has the benefit that we can do better checking at load time. And the one benefit of positional parameters would be less verbosity, but that's not the case for graphical programming languages like behavior trees. Our parameters may be made optional by defining a default value, and then the parameter doesn't have to be passed explicitly into the tree. Because reference node is actually our function call operator. It's also the place where arguments are evaluated. So the values for parameters are evaluated. And it's checked at load time that the parameters a tree requires are matched with the arguments that the reference node actually passes to the tree. Arguments are only evaluated once when the tree is entered and are never updated while the tree runs. That's to be consistent with how coroutines work or functions in the programming languages. It would be strange if they are updated throughout the function call. One more thing, we use so-called static scoping for parameters. That means that arguments or parameters are only visible to the tree that has them as a property and are not propagated to a nested tree. That can be demonstrated on a code sample at the bottom, where the parameter C is only visible inside a function f, but is not visible inside function g, even though the g is called from f. It may seem counterintuitive that we don't propagate parameters into nested trees, but propagation would be equivalent to so-called dynamic scoping, which is usually considered to be harmful or just not good for encapsulation and is usually considered to be hard to reason about.
So introducing the tree parameters, we've solved one problem, but there is always one more, as we all know. So what we have here is sometimes we just want to pass a value inside the same tree from one node to other nodes. So in the example at the bottom, that's just part of the top-level behavior tree that handles what waypoint should I be heading to. It gets the waypoint position, then it passes it through the parameters to the move subtree, then it waits a couple of seconds to look around at the waypoint, and then we increment the waypoint number to move to the next one. So really simple, and I just need to pass that one number between the three nodes. I can't do that at the moment. So again, I would have to revert to Blackboard, which pretty much shares the same drawbacks as we've seen with the parameters. So I couldn't store more waypoint indices, or I would have to have complicated variable names. So it would again lead to error, lead to bad encapsulation. And there's different use cases of that in the real behaviors that we use, like firing target is something we need to store often, or current movement position or engagement ranges. There's a lot of these examples. We could, of course, not store anything and just recalculate every time, but that's obviously bad for performance reasons. In target selection, for instance, you usually have to do a lot of visual checks and a lot of logic decision for what we actually want to shoot at. So we need a better solution, and that solution is local variables.
Okay, so to make it simple for designers to store only values that are relevant for only a single tree execution, we introduced local variables. Local variables are always initialized to a user-defined values, and they can be later modified. Again, same as for arguments, we use static scoping, so variables are only visible to the tree that defines them and are not propagated to a nested tree. That's again demonstrated by the code sample, where the local variable m is only visible inside f and not inside g. We initialize local variables in the reference node. That may not seem to be... No. Keep it.
No, keep it. All right, sorry.
Okay, it may be better to initialize them separately in some behavior tree scope for local variables decorator, but we have decided to merge the initialization of local variables with the initialization of arguments. but it requires us to have the ordering right. So at the code sample we can see we have some kind of scope for a tree, which means it's a set of arguments and local variables. And to initialize nested scope arguments, we can use the whole scope of a current tree. But to initialize locals, we can only use the nested arguments, because we don't want to propagate symbols from the outer trees.
Mm-hmm. So after all of these improvements are incorporated into our example, we have the resulting 3 trees. So we have the top level decision-making behavior tree, and then on the side we can see the 2 implementations of the firing and movement respectively. So we see that we've reduced the tree size quite a bit. We've also increased readability, so I can just look at the chunk, see what it does. I have the separation of concern that I wanted, and with the parameters passed explicitly through the reference node, I have nice compile time checking of if all of my references are correct, if they have the parameters they need. So it's a simple system for a designer to use, less error prone. An interesting fact about this particular example is where we started with 6 blackboard or global variables in the beginning, we have been able to reduce it to 1, which in this case is just the list of waypoints that the soldier remembers to patrol around. A little bit on evaluating this system, because as I've said, we use it currently on our project. So we've been able to deploy it in under 3 months, including training up the designers to be able to use the new features. We had an FSM-based system originally, so this included training up the designers to be able to use behavior trees in general. We use it to develop doctrinal AI for our military simulations. So that means the AI has to be fairly predictable. It has to do very specific things at specific points. And in our current system, we have over 100 behavior trees that use the reference node and the local variable concepts very heavily. So in the whole system that simulates up to company level AI down to an individual soldier, we, for instance, have just 1 behavior tree that handles engaging an enemy target. And it's fairly small. It has about 10 nodes, and the parameters and local variables make it variable enough that it's useful for all the different use cases that we have in our project. So what are the advantages of the system? I've mentioned a lot of them already, but we see them here in one place. The code is easy to maintain, just like any well-structured code. There's a separation of logic that's very useful if you have a team of people working on it. So we do have a team of about 5 designers working on the same behaviors at any given time. And the code, even on a large project, remains readable, which is always a challenge in a visual programming language. There are some disadvantages, of course. It's a bit more to learn for the game designers to understand when to use the parameters, when to use the blackboard, when to use the local variables. But the features are optional, so for simpler use cases, you can just omit them and use the normal behavior trees. There's a little bit of a runtime cost, but it's not very big, worth mentioning though. And of course, it's more difficult to roll out than just a basic behavior tree system. But as I mentioned, we've been able to do it in under 3 months. So again, nothing too bad.
The features mentioned so far are not the only features we want to have in behavior trees. For example, it would be nice to not only have per tree local variables, but to have local variables a bit more tight in smaller scopes. Like in the code sample at the bottom, the local variable C is only visible inside that if statement and is not visible elsewhere in a function. Another feature we already have a plan to implement is a dynamic dispatch. That means to be able to select the tree to be called depending on some runtime property, for example, entity type or world state. This would be inspired by how virtual functions are implemented in programming languages. And one more thing that would be nice to have is some kind of automatic cleanup. We have already tried to implement this in past, but it was the one feature that we didn't took inspiration in programming languages, and it ended up as being hard to use for our designers. So next time when we implement this, we should really get inspiration, for example, how C++ destructors work, or the dscope statement, or in other languages. We are also not the first one to come with the idea that trees can have parameters. After we have implemented our system, we have found out that there are already papers on the topic, and we also take inspiration in other major behavior tree engines and how they work. Thank you for your attention. Are there any questions?
Fantastic. Thank you very much for an interesting presentation. I have one question, that is, how do you handle constraints between the behavior trees when you split them out? I mean, one instance could be, you know, if you cannot fire beyond a certain speed, how do you handle that, you know, movement and fire behavior trees actually can take that constraint into consideration?
The same way as it is handled natively in the behavior trees. So the node that cannot be executed simply fails, reports the failure up to the one level. So if it's, for instance, called from a reference node, then the whole reference node it does fail, and if there's a selector above it, it takes a different behavior. So basically, we just propagate the failure of the behavior that failed.
Hello, thank you for the talk. Actually, I have no question. I just want to add to a discussion that for us in CD Projekt Red, the deparameterization is the most important core feature in our AI system. Is the way we build resources and stuff. I just wanted to say that for us also it's extremely important thing.
All right, cool. We should catch up afterwards and discuss it.
Questions, remark? So there's been a lot of traffic on Twitter on this talk, so maybe people want to chime in?
Hello. So I've noticed, like you mentioned, you have 100 trees. That's actually a lot. I guess, like what you call, that's my magnetic personality. And I guess like those, what you call reference nodes, which are basically subtrees, are within that 100, right, number?
Correct. So what we understand is one behavior tree is just one tree that can be called as a function or be used as the root tree.
So my question is basically if you had, because currently your reference nodes are kind of statically linked, like you just set, like this reference node is that subtree and that's it. If you had a behavior tree node that was like allowing you to select the subtree dynamically or being parameterized depending on the AI type, would that significantly reduce the number of behavior trees you have?
I don't think it would significantly reduce the number of behavior trees because we would still need to implement the different end behaviors, but it definitely adds ease of use to the actual, I need to now select a parameterized behavior, so it would replace a lot of trees that just pick between different references. So maybe that's what you're aiming at. And yes, we've considered this, and it's one of the future improvements that we are considering to come up with a system like that.
My name's Matthew Jack. I work at Kythera. We have a behavior tree implementation which similar to yours in some respects, I think. Thanks for the awesome talk. It's really good to see behavior trees talked in terms of as a programming language. I missed the very beginning, but are your blackboards only flat, or can you have blackboards within blackboards, nested blackboards? You do have that?
Yes, we have hierarchical blackboards.
Okay, so did that help at all with the scoping issues?
Yes, it would help in some respect, but you don't know which scope you should go into if you are just running a subtree, because you can run that subtree in a parallel node multiple times at once, so it wouldn't actually help that much.
So they're always shared between entities, or?
The blackboard is per entity.
Okay.
It's only.
Okay. And did you experiment at all with kind of stacked scopes? I think that's kind of part of how we solve some of these problems, by introducing another level of blackboard, like you, a stack of them to bring in the local variable scopes.
Yes, but still it's a global variable, and you need to follow some kind of discipline and how you should do stuff. But with our system, it's all automatic, and you cannot do mistakes that easily.
Okay, thanks very much.
Hey, so did you utilize a tick or event-based approach? And if you tried both, which did you find worked best with the designers? To recalculate what actions to take, did you basically calculate every tick, or did you have events raised to basically recalculate the subtrees?
We evaluate the tree from the top each frame, or each evaluation.
Okay, so you've not sort of wandered down the event-based path?
No, it's not event-based.
Okay.
Just on this topic, there is a BT talk also about with event-based BTs this afternoon, I guess.
Hi, yeah, I was wondering if, with behaviour trees becoming more like programming languages, I was just wondering how your designers were coping with the complexity. Because in my experience, only the most technical of designers were able to deal with building behaviour trees anyway. And there's sort of a cut-off point where those designers are so technical they could have just written code in like a scripting language anyway.
Thank you. That is a very good question. It's not much of an issue for us, because traditionally in our company, designers were always technical to some degree, because we add a lot of gameplay features in just our scripting language. So to us, it makes sense to view behavior trees more as a visual scripting language, as an easier way to script the behaviors. And yes, it puts some strain on the designers that they need to have some level of technical knowledge. But if the tools are right, and if we keep the complexity at a manageable level, then it's, in my opinion, the benefits outweigh the disadvantages of the designers having to learn new concepts, or sometimes producing less than optimal code. It's a lot about cooperation between the programmers and the designers as well in that respect. But the quick feedback loop of the designer being able to tweak everything in his behaviors by himself and seeing immediately the end results that he wants to achieve, for me, outweighs all of these concerns.
Hello. First of all, thank you so much for your talk, because it's parameterization, I think, has always been a really big problem for me, for behavior trees, and I found your talk really, really useful. And I would like to know if you could elaborate on how you get your communication with the rest of the systems. Like, do you have any, for example, animation feed, like events from animation within behavior trees, or are you working in totally different manner?
We don't solve animations in behavior trees.
I mean, do you have any, like when you have any animation event, do you get it in a behavior tree, or?
Maybe not for the animation events at the moment, but we do have a system that we call the message system, and that's basically an event handling and event raising system that you can both trigger events from the behavior trees, but also the simulation, the engine triggers events. Let's say when a shot was fired on you, or when you spotted an enemy. And I imagine the animation system would use the same concept of raising events in the behavior trees that you can then react on.
Any further questions? Okay, thank you guys. It was a great talk.